Welcome, Calculus AB. This is lesson 3.5, related rates. Let's begin. So this is going to be kind of difficult here, and we're going to have to do a lot more practice in class, but please try to follow along with some of this. So this is about story problems or word problems, and we're going to do some differentiation in those kind of problems. Like we have some scenario going on here, and we differentiate with respect to time, and we start talking about like the rate of change and stuff like that. And it's kind of fun to do, and I think it's kind of cool, but it's about like figuring out what you're actually supposed to do in these problems. So you have the idea of finding a rate of change of variables. So like the rate of change of the area, maybe the area of something is shrinking or growing, or the radius of something, or the height of something is shrinking and growing. And we have to look at a lot of the variables and figure out, you plug things in and figure out what kind of equations either we know or we can figure out just to solve for what the question's asking. So here's the kind of procedure to do these kind of things. And sometimes some of this information is given, and sometimes you have to figure it out yourself. So first you want to draw a figure if you don't already have a picture. Sometimes looking at a picture of something is good. Like if it's a picture of a circle growing, I would draw the picture of the circle and start labeling parts. And then start labeling any variables or any numbers that you know stick to be constant. And then write your given information down, and what you have to find. So if the radius is 5, write down radius is 5. And if you have to find the rate of change of area, write rate of change of area. And anytime you're using your rate of change, make sure you use the d of dt. So rate of change of area would be like dA over dt. Rate of change of height would be dH over dt. So rate of change, you're using a derivative symbol like that. And then you want to write some equations. So sometimes you're actually given equations, but sometimes you have to kind of figure them out. And you have to figure out your variables too. And I like this rule. Some variables are like going to stay, like the height of a ladder might stay the same all the time. So you have to think about, is that actually going to be a variable that's changing, or is it going to be constant? So if some quantity is going to be changing, we represent it with a variable. But if it's something that's going to be constant, we just write the number in. Like the ladder example I was saying. Sometimes you have a ladder problem. Well, if the ladder's not ever changing size and it's 10 feet, just make it a 10. Don't make like a variable L for ladder. You have to think of those quantities. Is it always going to be the same, or is it going to change? And then you sometimes look for secondary relationships, and this is about reading the problem. Sometimes you can actually create a second equation. And at some point, we're actually going to do our implicit differentiation on both sides with respect to t, which is what we learned in the last class. And then we just substitute and solve. And then we usually want to write what it actually means in real words. So let's do an example. Oh, and sometimes we have formulas. So a lot of times it's geometric shapes. Sometimes they give you formula, like I don't expect you to have memorized the volume of the sphere. But things that you should know, and you should know is circles, any right triangle or triangle area, and the Pythagorean theorem. You should know this. Volume of the cone? No. You should know rectangle formulas. You should know cube formulas, that the volume is side cubed or area is side squared times 6. I mean, you can figure that out. But things like sphere and cone, you don't have to know. Usually that would be given to you. So let's do an example. So this is like basic, not the word problem. Let's just work on a problem. So we're given our information already. And so we have some given information. We have a dx dt equals 6. Why am I rewriting this? We know my y equals 4, and then we have a function or equation, x times y equals 12. I want to find dy dt. All right? So I'm going to take this equation, x times y equals 12, and I'm going to do my implicit differentiation with respect to t. That means that, you know how before we only had to do like the y primes at the end, or the dy dx's? Well, you're going to have to do that for x's and y's. You're going to do dx dt's when you differentiate x's, and dy dt's when you differentiate y's, because you're differentiating with respect to time. Something's changing with time. So if I'm doing this equation, it's going to be a product rule. We're splitting that in f and g. So my f prime is going to be 1. It's going to be 1 times dx dt. So I'm just going to say dx dt. And my g prime is going to be 1 times dy dt, or just dy dt. So writing that out in my implicit differentiation, it's going to be f prime, so dx dt times y plus regular f times dy dt equals 0. So I did my implicit differentiation. Now I want to plug things in. Again, I want to solve for this one. I know my dx dt equals -6. I'll say -6. And my y equals 4 times 4. But my problem is, what's x? So this is not given to you explicitly. But since you know y equals 4 and you have this equation, I'm going to take that equation and say x times 4 equals 12. So divide by 4 on both sides, x has to equal 3. So sometimes some information is not given to you, but you can figure it out. So I'll say 3 times dy dt equals 0. And so this will be -24 plus 3 dy dt equals 0. And add 24 to both sides, so 3 dy dt equals 24. So dy dt, when you divide by 3, equals +8. And that's it. So that's without a word problem. Let's do one with a word problem, and then we'll do more in class. So we have a windlass, which is a boat. No, it's not a boat. A windlass is kind of like a rope, like a pulley right here. Think like a pulley. It's used to tow a boat to a dock. So this is your dock. The rope is attached to the boat at a point 15 feet below the level of the windlass. So there's a rope that's attached to the boat. And this level is 15 feet below. That's why it's 15. If the windlass, so this pulley, pulls in rope at a rate of 30 feet per minute, at what rate of the boat approaching the dock when there's 25 feet of rope out? Write a sentence explaining the meaning of your answer. Okay, a lot of information here, right? So, and they drew this picture for you, which is kind of nice. You have a pulley that pulls in this rope. What happens when you pull in this rope? This boat gets closer to shore. This is where the shore is right here. So it's getting closer to land, and this is all water. This is like water over here where X is. So that's, I'll draw some waves. So this is water, and that pulley pulls it in. Now, this is always going to stay 15 feet high. It's like a pulley that's up here in the sky, and that's just pulling that rope in. Okay, so this rope isn't going to stay this length forever. It's going to actually shrink as it gets pulled into this windlass right here. So let's write our given information. So we know this is 15 feet high. And we put some variables in here. Since the rope is going to change the length, we just wrote the rope equals z. We just put a variable. And the length from the boat to the shore, we're just going to call x. All right? X-axis kind of makes sense. And we don't have to put a variable here like a y because we know this is always 15 for the height. Okay, so given that information, we have this thing right here. If the windlass pulls in the rope at a rate of 30 feet per minute. So when you have this word rate, that's a key thing here. That means that the rope is coming in at a rate of 30 feet per minute. So the rope is coming in. So I'm going to say that's the rate of change of z. So dz dt is going to equal, it's coming inside. So that means it's getting shorter. So I'm going to actually say it's -30. If it was like getting longer, I'd say positive, but -30 here. At what rate is the boat approaching the dock when there's 25 feet of rope out? So what rate is the boat approaching the dock? So that's going to be the rate of change of dx dt is what you have to find. So that equals, I don't know. This is what I'm trying to find. And it happens when there's 25 feet of rope out. So when z equals 25. Okay? So that's all my information I have. Now, I don't have an equation, but you have this shape here that's a right triangle. And you know with the Pythagorean theorem, I could say 15 squared plus x squared equals z squared. All right? So that's my equation. I'm going to do my implicit differentiation right here. So derivative of a constant squared is just 0 plus 2x times dx dt equals 2z times dz dt. All right? Cleaning that up a little bit, I can actually divide by 2 on everything too. And I'm going to get x dx dt equals z dz dt. All right, now I'm going to plug things in. So the problem is I don't know my x. So I can plug in my z. Let's plug in what I can. 25. And I know my dz dt equals -30. And I'm trying to find my dx dt. But I don't know my x. But I do have this equation. And I'm looking at the case when z equals 25. So I'm going to plug in this, and I get 15 squared plus x squared equals 25 squared. Now I can use that to solve for x. So this is 225 for the 15 squared plus x squared equals 625. Trust me. And so you subtract 225 on both sides. And what you're going to get is x squared equals 400. And then you square root both sides. So you get x equals plus or minus 20. That's the square root of 400. So it's two possible answers, positive 20 or negative 20. And sometimes this might happen, especially with squares, but you have to think, what is a realistic answer? I mean, this is x. It's not going to be negative. So we got to do the positive answer. So my x equals 20. So I'm going to put a 20 in for the x right here. Now, if we did that work, I don't have room right there. I got to do my little extender, page extender. Sorry, page extender. Okay, page extender. So 25 times 30 is going to be negative 750, I hope. Goes 20 dx dt. And you're going to divide by 20 on both sides. So you get your dx, dx dt equals negative 75 halves. I'm going to leave it as that. I'm not going to put it as decimal. Now, the other thing here is we have to talk about units. I am talking about feet, and I am talking about minutes is my time. So our rate of change is just going to be feet per minute, because it's one dimension. So what this says is dx dt is negative 75 over 2 feet per minute. That means the x is changing at a rate of the distance of the boat to the shore is changing at a rate of 75 halves feet per minute. I could say that. All right, we'll do more in class.